Let's do an example of a 3D truss problem, similar to the types of problems you'll see in your homework. The problem I've selected, which depending on which version of the textbook you have, you may find in your textbook, is a 3D truss that consists of 3 bars indicated here in blue. A bar here, here, and here. At each end of the bar, at one end of each bar, is a pin attached to an immovable wall. So this point of the bar, this point of this bar, and this point of this bar is not free to move in any direction. The problem statement gives us a global coordinate system. Our global coordinate system is indicated here with an origin at this pin joint, and we're given the location or the orientation of the x-axis, y-axis, and z-axis. At the point the 3 bars meet, a force is applied of 20 kilonewtons, and we're told in the problem statement that the force of 20 kilonewtons is applied in the global x direction. We're given the modulus of elasticity of each bar element, and we're also given the cross-sectional area of each bar. Now, the problem goes a little bit further and actually gives us some information that's usually left to step 1 of our problem solving. It gives us some of the discretization. So we're told in the problem statement that this entire bar will be our element number 1, this entire bar will be our element number 2, and this entire bar will be our element number 3. We're also given node numbering. We're told that we're going to call this node number 1, we'll call this node number 2, we'll call this node number 3, and we'll call this node number 4. The problem statement gives us the location in 3-dimensional space of each node. So, for example, obviously node number 2 is located at 0, 0, 0 in the global coordinate system. What are we asked to find? We're asked to find the displacement of node number 1. Keep in mind, node number 1 exists in 3-dimensional space. It's free to move in all 3 directions. Therefore, I expect its displacement to have an x component, a y component, and a z component. We're also asked to find the stress in each bar. As engineers, that's probably what we're interested in because we want to know whether our truss is strong enough to actually support a force of 20 kilonewtons applied in the x direction. All right, so what's left for us to do as far as discretization goes? In order to form the local and global stiffness matrices, which we will do in following videos, not only do I need the modulus elasticity and the cross-sectional area, I also need the length of each bar element. I wasn't given the length of each bar element. I'm asked to find that for myself. I'm also not given the angles that relate the local coordinate systems. Remember, each bar element will have its own local coordinate system to the global coordinate system. Remember, each bar element will have its own local coordinate system with an x hat direction along the length of each bar. I need to find the angles theta x, theta y, and theta z that relate that local x hat axis to the global coordinate system. And that wasn't done for me. So let's go ahead and do those 2 things. Let's first find the length of each bar element. In order to do that, I can take advantage of the distance formula. So to apply the distance formula in this case, what I want to do is I want to find the differences for each bar element, the differences in the x component, square that, the differences in the y component, square that, and the differences in the z component, square that. Take those 3 terms, sum them together, find the square root. That's the length of that bar. So, for example, to find the length of the first bar, L superscript 1, that'll just be the square root of, let's see, 0 minus 12, 0 minus 12 squared plus 0 minus minus 3 squared plus 0 minus minus 4 squared. And if I go ahead and I plug that into a calculator, I'll get the length of L1 is 13 meters. Doing the same thing for the other 2 bar elements, I will find that the length of L2 is 3 meters and the length of L3 is 10.05 meters. All right, so that's the length. Now I need to find those angles. Now, finding those angles might be a little bit tedious. Luckily, we don't need to find the angles themselves. What we need to find is cosine of those angles, because if you remember in the formula for the local stiffness matrix, which I'll show in the next video, we're only ever using the cosines of those angles. Finding the cosines of those angles turns out to be a little easier than finding the angles themselves. I want to complete this chart. So I need to find cosine x, cosine y, and cosine z for each bar element. To do that, remember cosine is just adjacent over hypotenuse. The hypotenuse is the length of each bar element. The adjacent length I can use, it will just be the difference. In this case, for example, to find cosine x, it will just be the difference between the x components of the two nodes at either end of each bar element. Now, when I used the distance formula, it really didn't matter if I was calling this node number 1 or this node number 2. It really didn't matter which order I did the difference in, because I was going to square each term anyways. But with angles, remember sine is important. So the rule of thumb you always want to use is you want to go from the higher numbered node minus the lower numbered node. So example, this cosine x for bar element number 1 will be 0 minus 12 over the length 13. So I will end up with negative 12 over 13 as cosine x for that bar element. Following a similar pattern, I'll have 0 minus 3, so I will get a positive 3 over 13 for theta y, and I will get a positive 4 over 13 for cosine of z. Going ahead and doing the other two elements, element number 2 is easy because it's parallel to the z-axis, so cosine of theta x is just going to be 0. I'll get another 0, and for cosine of theta z, I will just get negative 1. For bar element number 3, I'll end up with the difference of 2 over the length 10.05, 9 over 10.05, and 4 over 10.05. All right? And I could fill out the rest of this chart. I was given the modulus elasticity for all 3 bar elements. I was given the cross-sectional area. And for the length, remember, I found was 13, 3, and 10.05. If you can't read that, don't worry. I'll have this typed up in the next video where we will find the local stiffness matrix for each bar element.